So let's now discuss the first order differential equation, the linear differential equation types, and basically how to solve them. Differential equations, and we are basically discussing first order type. So this will be first order. So basically a linear differential equation, the first order differential equation is generally of this form. Where you have the dy by dx term and the y terms separately, and the coefficients can be either constant or functions of x and y. Now remember that p of x and q, basically capital Q, are only functions of x. Functions of x or constant. It can be constant or function of x. Okay, so that is the basic thing. Okay, and this becomes a homogeneous first order linear differential equation if your q of x is 0, and non-homogeneous, these are all something which we have seen during the classification of linear ODEs. It's not equal to 0. So how do we solve them? Well, there is good literature, good mathematical literature about these linear differential equations, and the standard method is basically the integration factor method, which we'll discuss how. We'll not derive how this method has evolved, but basically how this method solves a differential equation, a linear differential equation, we'll see. So integrating factor IF is something given like this: e power p of x t of x. So once if I am able to find out the integrating factor, then the solution for this linear only is that y into integrating factor IF is equal to integral of q into IF dx plus c. Okay, so this is the solution, or you may have the other way around. Suppose dx by dy is equal to, dx by dy plus p of y into x is equal to q. Then the integrating factor is basically e integral p of y dy. So x has replaced with y has replaced with y. That's the thing. And now the solution in this case is x into integrating factor is equal to integral q into if into dy plus c. So these are the these are the two ways in which it is also. Most of the time it is in this form. Okay, and so the only idea is to find out the integrating factor and then just solve the differential equation. So we'll solve a couple of examples in order to understand this better. So let's solve some examples in order to understand this linear differential equation. So we have not derived anything, we have just told you the solution, the form of the solution. Once you calculate the integration factor based on the linear differential equation, and the form of the solution is known. So let's solve one example in order to understand this. Example 1, where you have dy by dx minus 2y by x is equal to x square. So comparing with that standard form whatever we have derived, so p of x is basically minus 2 by x, and q of x is basically x square. So the integrating factor would be e integral p of x dx, okay, which will be e to the power of minus 2 by x dx, and this can be written as e minus 2 ln x. Okay, and minus 2 goes there, so it becomes e ln 1 by x square. Okay, and you know that e power ln to the base anything, to the base e, but the value, so e power ln a to the base e, will be basically a only. So similarly, in this way you can then write this as 1 by x square. So this is your integration factor. So now the solution is quite simple. Y into integrating factor, which is 1 by h square, is equal to integral q into, so q is h square into integrating factor, that is 1 by h square into dx plus c. So this can be written as h square it cancel, integral dx plus c. Integral dx is h plus c. So y into 1 by h square is equal to integral h plus c. So now this can be written as h square can be taken out common. So I mean multiplied both sides. So c h square. Okay. So this is basically your solution for the given differential equation. So this is quite simple, but I mean this method only applies when you have a linear differential equation, which is mostly the case. Okay, so let's solve another example. So let's solve another example describing this linear differential equation. Okay, so example number 2, where you have dy by dx plus xy is equal to x cube. So comparing with the standard form, p of x is x and q of x is x cube. Okay, so now the integrating factor will become e power integral p of x dx, which is nothing but e power x dx, which is nothing but x square by 2. So this is your integrating factor. And now the solution is y into integrating factor is equal to integral q into integrating factor dx plus c. So just substituting it, y into e power x square by 2 is equal to integral q is x cube and e power x square by 2 dx plus c. Well, now we have the task of evaluating this integral. So how do we evaluate this integral? Now say suppose if I consider u as x square, let's say, in order to evaluate this integral. So du will be 2x dx. Okay, so this integral x cube e power x square by 2 dx will become, substituting in terms of u, it will be h square will be u. Okay, and the remaining h dx will come from this, which is du by 2. Okay, and e power h square by 2 is e power u by 2. So that is the thing, e power u by 2, right? Okay, now this looks something like integration by parts, but for that we need to again, let's substitute v as e power u by 2. Let's see what happens if we substitute v as e power 2. So this will become dv as e power u by 2 1 by 2 into du, right? Into the internal derivative, which is derivative of u by 2, it is du. Okay, so it will be half e power u by 2 du. So let's substitute back, and so what we will get, or I mean what I mean to say is that, okay, let's not substitute this, let's not do this way. We'll directly apply integration by parts, and integration by parts you can apply in many ways. So if you have two functions, f of g as a function of x, f is a function of x, g is a function of x. Okay, then this integration by parts can be written as f of, I mean both f and g are function of x, minus, so this need not be written, I mean this is default, minus integral f dash x integral g dx. So this is the general form, and the priority here goes in this form, like the priority which what f should be goes in this form. If it is an integer or logarithmic or algebraic or trigonometry and exponential, so in this order of priority you should take the function for f. Okay, elite, this is the general order of priority for function f of x. Okay, now so from this we can take f as u, and anyhow exponential has the least priority, so that can be taken as g, and g is u by 2 by 2. Okay, so now just a 1 by 2 you can just take out constant throughout. I mean, that will be something. So g is e power 2. So now by this method, half is something common. So integral u e bar u by 2 du will be basically u into integral u by 2 du minus integral f dash x. So du by basically derivative of u, which is 1. Remember, x is u here when we have just applied integration parts, and integral g is e power u by 2 du, right? Okay, so e power u by 2 integral is e power u by 2, and the by of internal derivative, which is 1 by 2, which is a constant, minus integral e power 2 integral is e power 2 1 by 2 du. And now if you just integral this, so 2 into, and the integral of e power 2 is e power 2 by again 1 by 2. So this will become 2u e power u by 2 minus 4 e power u by 2. And so substituting it back in this expression, what we get is, so integral x cube e power x square by 2 dx is equal to half integral u e power u by 2 du is equal to half. This value will come, and now you can always substitute as x square. So this will be u, so 2 will go x square e power x square by 2 minus 2 x square by 2. So this is how the integrating constant will look like. Okay, so now substituting it back in the given thing, so the substituting back in the given thing, the final solution looks like this: y into e power x square by 2, and then the integral which we evaluated, which comes out to be x square e power x square by 2 minus 2 e power x square by 2 plus constant. So this is the solution for the differential equation. So this method is quite popular. The linear differential equation method is quite popular. Okay, so now let's see one of the extension of this linear differential equation, which is the Bernoulli equation form. Okay, which is basically the Bernoulli equation form. So what will happen, and just an extension of this Bernoulli, the linear equation, or you can say the equation reducible to the linear equation. Okay, so what will happen if we have something like this: dy by dx plus py and q, and say you have y in power n. So this y power n is additional. So in this case, what you will do is you will divide by y power n throughout. So it will be y power n dv by dx plus p y by y power n is equal to q. So this will be basically y power n dy by dx is equal to plus p, basically plus p 1 by y power n minus 1 is equal to q. So now if I substitute, let's say 1 by y n minus 1 as v. Okay, so this is basically something like this. And now if I differentiate with respect to x, so this will be minus n minus 1 y minus n minus 1 minus 1, right? This is the general form, right, into dy by dx. That's what you do. And y is a function of x, so y power n will be n into y n minus 1 into dy by dx is equal to dv by dx. So all this, if you substitute back in the unit version, so let me first simplify before going substituting it back. So this will be y to the power of minus n plus 1, so this will be minus n dy by dx is equal to dv by dx. Okay, or you can write 1 by y power n dy by dx as minus n minus 1 dv by dx. So this is the general form which you can. Now substituting it back, this expression and this expression in the given differential equation. So this term we have already derived, so it comes out to be something like this, plus p is your constant, I mean function of x, and this is v q. So now you can observe that n minus 1 is a constant. Okay, so this is basically a linear differential equation in v. Okay, so this is a linear differential equation. Only thing is the dependent variable has got changed. So now we can just use the method discussed just previous just previously. I mean the method just discussed previously, that is the linear D method we can use. So something of this order can also be brought into a linear form. Okay, so let's see one example solving this. Solve and another example, dy by dx plus y is equal to xy square. Okay, so this you have this y power n term constant, so just divide by 1 by y square. So this will become y square dy by dx plus 1 by y is equal to x. So let's put v as 1 by y. So obviously v as y power minus 1. If you differentiate with respect to x, dy by dx is equal to minus 1 y minus 2 into dy by dx. Okay, so basically from this what you will get is y square dy by dx as minus dv by dx. So substituting this and this back in the equation, we'll get minus dv by dx plus 1 by y as v is equal to x. Okay, and this can be written as minus v is equal to, I mean sorry, this no is equal to here, minus v is equal to minus x. Minus v is equal to minus x. Okay, so now the integrating factor for this will be, this is a linear equation, linear differential equation in v. So the integrating factor will be e integral p dx, which is e integral p is 1. Okay, so p of x is minus 1 and q of x is minus x dx, so that will become e power minus x. Okay, so the solution is y into integrating factor is equal to integral q into integrating factor q into the integrating factor, which is q of x is minus x, the integrating factor is e power minus x dx. Okay, plus some constant. So this can be written as minus e power minus x dx plus c. Okay, and now this is again integration by parts. F of g d of x is f integral g of x dx, I mean g of dx, g into dx minus integral f dash integral g dx dx. So something like this we can evaluate. So basically integral x e power minus x dx, so this is by parts. Okay, integration by parts. So x into e power minus x dx minus integral f dash x is df by dx, which is 1. Integral g of x dx is simply minus x dx dx. Okay, so this will be x into e power minus x, integral is e power minus x by minus 1, minus this will be e power minus x by minus 1 dx. So minus x e power minus x minus, so minus and minus will plus become, then e power minus x again you have to integrate, which is minus 1. So this will be minus h e power minus h minus e power minus h. Okay, now substituting that here, the integration solution is plus h e power minus h plus e power minus h plus some constant. So just if you if you just multiply e power minus h throughout, you will get x plus 1 plus some c into e power minus h. So this is, e power minus h, you're just multiplying e power h throughout. So that's the thing. So it will become y is equal to x plus 1 plus c into e power x. That's hold on for a second. This was basically v. There's a slight mistake. So this was a differential equation in v. So we'll be getting v here, and that's for this is v here, and this is v here. Okay. So just only thing is we have to just substitute it back. Okay. So only thing is, so whatever we got was x plus 1 plus c into e power x. Okay, so y, we know that v is 1 by y, so 1 by y is equal to x plus 1 plus c into e power x, and y is equal, so this is how, or y you can take out, you're going to multiply, so this is how you're getting the, so this is the solution basically, or you can, you can put in this form as well, whatever form you want, you can put, okay, this is the solution of the differential equation. Okay, basically the Bernoulli equation which we just reduce it to the linear form. Okay, so now let's come to the last method, which is the exact equation method. Okay, so let's see what it means. Okay, so the requirement of this method is that a first order differential equation expressed, which is expressed in the form as m x comma y, that means m is a function of x y, dx plus n x comma y dy is equal to 0, is said to be exact if basically the left hand side, LHS means this is the left hand side, is function, is basically the differential of a function phi x comma y. Okay, so what it means is, this is basically a definition of exact. So this, when you say this is an exact mdx plus ndy, you should be able to express this as a differential of this function. Okay, so something like this, d of phi xy will then become m x comma y dx plus n x comma y dy. Okay, so this is the differential, so this is the meaning. So this, so when you call this LHS to be an exact, it should be able to, you should be able to express mdx plus ndy as a differential of some function. Okay, so in this case, you can always say that if this is the case, then m is basically dou phi by dou x keeping y constant. This is what the definition goes, and n is dou phi by dou y at x equal to keeping x equal to constant. So this is a general partial differential, that is d phi. This comes from the fact that d phi is dou phi by dou x dx plus dou phi by dou y dy. So when it is exact, you can express d phi in this way. So comparing with that, m is dou phi by dou x and n is dou phi by dou y. So just to explain all this, let's take an example. Say you have something like this, x dx plus y dy. So m is x, n is y. So this is 0. So now this, whether it can be exact, like by inspection you can say that this you can write as x square plus y square by 2. So once you just differentiate it back, you will get 2x plus 2y, 2 is equal to constant. So I can write my phi as x square plus y square by 2. This is 0, sorry. So this is my phi. So sometimes by inspection you can find out phi, and therefore the solution is basically, the idea is if this is exact, so this can be written as d of x square plus y square by 2, or basically d of phi. And now if you integrate, you will get phi is equal to constant. So for example, so the solution for this will be, so this I can write in this way, and this I can write because it's exact. So this is just by inspection I can write in this way. So now if I integrate on both sides, I'll get x square plus y square by 2 is equal to constant, or basically implies phi is equal to constant. Phi is this x square plus y square. So this rarely exists. Sometimes if you have, the only thing is you have to bring the given equation in the exact form. Okay, by inspection it is very easy, that's what we have done, but then there should be some rules, right? Okay, so let's see how to check whether a given differential equation is exact or not. Yeah, how do you check? Well, this is again from the partial derivatives. Like if it is exact, you should be able to express in this form, right? And then the idea is then your the mixed partial derivatives, basically dou square phi by dou x dou y, or dou square phi by dou y dou x should be same, right? The mixed partial. So from that we can get a condition for exactness. So let's write it out. A necessary condition for exactness of the differential equation mdx plus ndy is equal to 0 is that your dou m by dou y plus, basically the dou m by dou y should be equal to dou n by dou x. So that is the condition. Basically means that because if you substitute m as dou phi by dou x in that condition, and n as dou phi by dou y, so it basically means that the mixed partial derivatives dou square phi by dou x dou y has to be equal to dou square phi by dou y dou x. Okay, basically it means that this has to be equal. Okay, the partial derivatives of phi has to be equal, that's what it means. Okay, and so these are the conditions. Okay, and this we know that for a function to be continuous phi, okay, the mixed partial derivatives are equal. Okay, so that's what the basic thing means. So you, if you are able to, so given a differential equation, you know what is m and n, and if you are able to check that dou m by dou y is equal to dou n by dou x, then it is exact. And once it is exact, you know that it can be expressed in a differential format. Differential of some function is equal to constant, and then you can just integrate. So once it is exact, we can easily find phi. So we'll see how to find out phi, because once it's that, you know that dou m by dou y is some constant, and dou m by dou y is, and dou n by dou x are equal. So from that you can we'll see how to find out phi here. So we'll take an example here. Verify that the differential equation 2x plus sine y minus y e power minus x dx plus x cos y plus cos y plus e power minus x dy is equal to 0 is exact. So first we need to verify it is exact, and then we have to find its solution. Okay, so comparing with the standard form, m is 2x plus sine y minus y e power minus x, and n is x cos y plus y plus e power minus x. Okay, so let's just see, just because the necessary condition is that dou m by dou y is equal to dou n by dou x, so just find out dou m by dou y and keeping x constant. Remember this x is constant here. Okay, so x is constant, so just treat x as some constant. So this will become this, the derivative of this is 0. For this the derivative will be cos phi, and e power minus x is some constant, so integral only y is there, which is 1, and this will become e power minus. Now dou n by dou x keeping y constant. Okay, whenever you are doing partial derivative, it means the other independent variable is constant. Dou n by dou x will be keeping y constant, so cos, so dx by x is 1 into cos y is some constant. Cos phi is constant, so we will not get e power minus, so cos phi is constant, so this is 0. E power minus x will be minus e power minus x. Okay, so this you can just simplify, cos y minus e power minus x, and this also will be cos y minus e power minus x. So you can see that dou m by dou y is equal to dou n by dou x. So basically the given dE is exact. Okay, so once you know that given dE is exact, so now we know that m is dou phi by dou x. Okay, and m we, so basically I can write dou phi by dou x is cos y minus, sorry, dou phi by dou x is m, so m I can just put the m form, 2x plus sin y minus y e power minus x. Okay, and similarly n is dou phi by dou y, so from this we got, I mean, let me write here itself, dou phi by dou y is basically n is x cos y plus cos y plus e power minus x. Okay, so if this I integrate, okay, this I integrate, keeping integrate with respect to x. Okay, so I can get phi of x comma y is equal to integral 2x plus sin y minus y e power minus x dx. Okay, keeping y constant. So you remember you are integrating keeping y is equal to constant. So the constant function can be, the constants can be function of y. So this, if you integrate with respect keeping y constant, so this will be 2 into x square by 2 plus y is constant, so this will be sin y x, sin y into x, y is constant, so e power minus x is e power minus x by minus 1, plus the constant term can be function of y, so let's call c of y. Okay, let's call some constant of y, which can be constant of y or some constant. Okay, so this I can write, simplify, x square plus h sin y plus e power x plus constant of y. Okay, now how do I get this constant of y? Well, I have the other equation, so just substituting here. Okay, so let's substitute. So substituting dou phi by dou y will be basically on the left hand side you will be having, yeah, so let's substitute that dou phi by dou y. Let's use this x cos y plus cos y plus e power minus x. So whatever we got dou phi by let's substitute the function y. Okay, so this will be basically sin y, so x into cos y plus e power minus x, basically you're differentiating with y, then c dash, so basically c dash means dc by dx. Okay, so from this you can just cancel these terms. Okay, so you will get to know that c dash turned out to be a function, basically function of, so yeah, from this you can say that c dash turned out only to a function of y, because the original d is exact, otherwise the c of y, c dash y, would have had some function of x. Okay, so now this if you just integrate it, you will get what? I mean, now we need to find out c of y. Okay, so just integrating is integral cos y dy. It will be basically sine y plus some constant. Okay, and now if you just substitute it back in the given equation, so we'll getting phi of xy is equal to uh, phi of xy. If you just substitute it back, okay, so we'll be getting h square plus h sine y plus y e power minus x, and the c of y which we got is sine y plus some constant. Okay, so this is the general solution which satisfies. Now c, you can choose it to be 0 or some constant. I mean, even if you add some plus 3 or plus 4 to this x square plus h sine y plus y e power minus x plus sine y, it doesn't make difference. The differential equation is going to be same. So this is the one of the ways to find out. So to solve basically an exact differential equation first order. So just recollecting what we have done. First is identify what is m, what is n. After expressing it in the form of m dx plus n dy, and then check whether it's exact. So once it's exact, then you can do this process. So we have seen that in this example, dou m by dou y is equal to n by dou x. So it is exact. So once it is exact, now, and exact is nothing but we have seen what is exact and all that in the differential equation. Okay, so once you know that it is exact, now you can express it in the form of m dx plus n dy has to be some differential of phi. So how do we do is we just take dou m by dou y and integrate. I mean, we know what is m and n. We know what is m and n. We know m is dou phi by dou x, n is dou phi by dou y. So just take the functional form of m, integrate it, get phi of xy. You will get some constant terms of y, and now you have to use the other equation in order to get this constant function of y. That's what we did in this expression. Okay, now most of the time, and instead of going through this exercise, like if you are unable to express anything, I mean, if it's a big equation, you should always use the procedure we followed in this example. But sometimes, even by inspection, we can find out, like y x dx plus y dx. You can always write this as d of xy, right? D of xy. This I can always write. So always when you have something like this, you can always express d of xy and then integrate. Okay, and now the other of this, you can always write d of y by x, because this comes, if you go backward from here to here, this is basically the u by v rule of differentiation. So from that you can write. Similarly, something like this, if you have h dy plus y dx by xy, you can always put this as d of log xy, because it will be 1 by xy and then the differentiation of xy, which is x dy plus y dx. Okay, and similarly you have, so these are like, if you have directly in this form, you can always express by the right hand side. So h dy minus y dx by xy is basically a combination of this and this. From this you can think, and it comes out to be log xy. Similarly, you have h dy minus y dx by x square plus y square. So this comes out to be tan inverse of y by x, because you know that tan inverse of something, if you're differentiating, it will be 1 by 1 plus y by x whole square and then the internal derivative. Okay, so these are some common forms. Well, if you can bring your differential equation in this form, then you can always replace it by the right hand side. Okay, so we have seen, this is tan inverse, so we have seen exact, what is exact, how to solve a exact, how to solve, what is the necessary condition to check if it is an exact. Okay, so exact means basically all this. If something is exact, you should be able to express as a differential of some function. So we have seen what is exact, and if it's a complicated expression, you can always use the necessary condition for finding exact. And if you are able to find out what, if it is exact, you know that it is exact, then you have to follow the procedure which we have laid in the example just shown. And sometimes by inspection you can readily say that you can readily express differential equation in the form of differential. So that's what we have seen here, okay, in the inspection method. Okay, so these are all the, so now we complete the first order, how to solve first order differential equation. We have discussed four methods: the variable separation method, the homogeneous method, the linear equation method, and the exact differential equation method. So, and we have seen slight modification or slight extension of each of the method, and one example each. So now let's move to higher order linear differential equation.